Calculating the value of an electric field. In the example, the charge Q1 is in the electric field produced by the charge Q2. This field has the value in a newtons per coulomb NC. An electric field can also be expressed in volts per meter, which is the equivalent of newtons per coulomb. The electric force on Q1 is given by in newtons. This question can be used to define the electric field of a point charge. The electric field E produced by charge Q2 is a vector. The magnitude of the field varies inversely as the square of the distance from Q2. Its direction is away from Q2 when Q2 is a positive charge and toward Q2 when Q2 is a negative charge. Using equation, the field produced by Q2 at the position of Q1 is in newtons per coulomb. When there are several charges present, the force on a given charge Q1 may be simply calculated as the sum of the individual force due to the other charges Q2, Q3, etc. Until all the charges are included, the sum requires that special attention be given to the direction of the individual forces. Since forces are vectors, the force on Q1 can be obtained with the same amount of effort by first calculating the electric field at the position of Q1 due to Q2, Q3, etc. To illustrate this, a third charge is added to the example above. There are now three charges in location of the charges using Cartesian coordinates or respectively. From the sign of charges, it can be seen that Q1 is repelled by Q2 and attracted by Q3. It is also clear that these two forces act along different directions. The electrical field at the position of Q1 due to charge Q2 is just as the example above. Superposition principle. The calculation demonstrates an important property of the electromagnetic field known as the superposition principle. According to this principle, a field arising from a number of sources is determined by adding the individual fields from each source. The principle is illustrated by figure 3, in which an electric field arising from several sources is determined by the superposition of the fields from each of the sources. In this case, the electric field at the location of Q1 is the sum of the field due to Q2 and Q3. Studies of electric fields over an extremely wide range of magnitudes have established by the validity of the superposition principle. The vector nature of an electric field produced by a set of charges introduces a significant complexity. Specifying the field at each point in space requires giving both the magnitude and the direction at each location. In the Cartesian coordinate system, this necessitates knowing the magnitude of the x, y, and z components of the electric field at each point in space. It would be much simpler if the value of the electric field vector at any point in space could be derived from a scalar function with magnitude and sign.